delighted to have Mark from Raamsdonk from UBC tell us about cosmology via Holography.
Okay, well, thanks for the invitation. And I'm going to talk about a variety of things that I've thought about in the last few years. I've worked with a bunch of people on related topics, and so I think hopefully I didn't miss anyone. And so I guess the general thing that I've been trying to focus on for the last 5 or 6 years is trying to make some progress on connecting our models of quantum gravity that we've made so much progress on and our actual gravity that we live in our universe. So trying to come up with some model of cosmological spacetimes with big bangs and expansion. Oh, just made it.
That's a closer call than I am.
Okay, sorry. Thank you for your efforts. Raphael is coming from, where do you say, Germany? Frankfurt. Frankfurt, okay, so this is my first slide. So saying, want to come up with quantum gravity models of cosmology, and I probably don't need to motivate that for this audience, but there's, I think, a lot of questions in cosmology that we would really like to have something beyond effective field theory in order to be able to answer these questions. And so there's kind of a weird history of thinking about cosmology and string theory and quantum gravity. And so in 1997, we had these first complete quantum gravity models, I would say, with the ADS-CFT correspondence, and we realized how we could do quantum gravity in some situations with a negative cosmological constant, and this beautiful connection to say that these gravity theories are fundamentally defined by some underlying non-gravitational theory. And then, I guess 2 years later, then we noticed that our universe has an accelerating expansion, and at least the simplest explanation for that is positive cosmological constant. And so somehow after that, I think a lot of the discussion when you bring up cosmology in the string theory community, I think a lot of the focus has been on how do we realize models with positive lambda, either finding string compactifications, which give you positive lambda, or generalizing holography to positive lambda. So there's been a lot of work on this, and definitely some progress, but it feels like people have been trying this for the last 25 years, and the progress has been sort of slow compared to how much we've learned by doing negative cosmological constant physics. And so I guess my perspective on this is, well, why don't we just not worry about positive cosmological constant for now. Let's try to stick with the theories where we're making all this progress. And so think about quantum gravity theories with a negative cosmological constant. We understand how to describe at least asymptotically ADS solutions of those and relate them to some dual CFT. The very same gravity theories that we have all this understanding for have interesting cosmological solutions. If you just take an FRW ansatz in those same interesting quantum gravity theories, put in some matter and radiation, and then you have various cosmological solutions. And so I think a nice intermediate goal for learning about cosmology and how to relate that to quantum gravity is just to think about those cosmological solutions, describe those somehow, and understand whether that cosmological physics can be related to the physics of the associated CFT somehow. And so just to motivate that, I mean, this was an excellent strategy for learning about black holes. So we could have said, oh well, the black holes in our universe are flat space black holes. So let's just devote all our efforts to trying to think about flat space black holes. But in reality, what has happened in the last 25 years is we made all this progress in understanding black holes, but also quantum gravity generally by thinking about ADS black holes using holography. So I want to do that for cosmology. just, I don't know if I'll get to this by the end of the talk, an interesting thing that I've realized in studying all of this is that it might not even be just a purely theoretical exercise. So going in, I thought, okay, well, let's just do this, even though negative cosmological constant is not realistic for nature. But as I'll say at the end of the talk, I think actually these negative lambda models that might have holographic descriptions could actually be potential models for our own universe because these things actually also can give rise to acceleration in a natural way. But for now, let's just focus on the more theoretical questions of how can we describe cosmological physics somehow using CFT physics. Okay, okay, so the starting point is, pick your favorite holographic CFT, n=4 super Yang Mills or some, 2D one if you want to study 3D cosmology. And so whatever you've picked, then there's some gravitational effective theory that would be associated with that, where the operators in this CFT would be related to the fields in that gravitational effective theory. Okay. These gravitational effective theories would have ADS solutions that correspond to the vacuum state of these CFTs. And so since they have these ADS solutions, they would have some negative cosmological constant. The usual story that we understand is that we can then study various different states of the CFT on some geometry, and those tend to be dual to spacetimes that are what I call asymptotically empty and kind of asymptotically static. So we can describe lots of interesting stuff like black holes and gravitational waves and interactions between those and other kinds of matter. But that typically is in some localized region of an infinite space, and then if you go far away, there's nothing, and then it's static. And so that's quite different from what we want to do in cosmology, which is to fill the universe with stuff and study the evolution of that universe from a Big Bang. So how do we do that? Okay, so I guess the first useful thing to say is that these same effective theories, they have cosmological solutions. So they're a little bit different than the ones we often think about, because when you have a negative cosmological constant, that tends to give you a big crunch eventually. But early on, the cosmological constant doesn't really matter very much. Okay, so in starting from a Big Bang, if you have a certain density of matter and radiation, things proceed very much like they proceeded in our universe. And then it's only once the matter and radiation start to dilute because of this 1/8 cubed or 1/8 to the fourth. Eventually these terms get smaller, and then the cosmological term becomes more and more important. And so if we have a positive cosmological constant, that leads to acceleration. If you have a negative cosmological constant, then eventually this thing just cancels, so A dot is equal to 0. And so that means the universe has stopped expanding at all, and then after that it starts recollapsing. So that's your, if you just have a negative cosmological constant, matter and radiation, that's what you'll get. Okay, so that is a solution to an effective theory, which is somehow has an affiliated CFT. And then we'd like to know, well, if we want to describe the cosmological physics somehow in terms of CFT physics, is there a way to do that? Okay. And it seems it would be surprising if this, if these solutions are completely described by the physics of this dual CFT, but then this other solution of the same theory had nothing to do with the physics of the CFT. So I feel like somehow the cosmological solutions here also should have something to do with CFT physics, and we just need to understand how do we relate it to the CFT physics. Okay. Right, so why isn't it, why don't we just have some CFT state that's dual to the cosmology? And so, like, one challenge, if you think about those Big Bang, Big Crunch cosmologies, they're not really asymptotically ADS. So there's not like a place where the CFT would live. If you look at the space-time diagram for a typical Big Bang, Big Crunch space-time, it's sort of like this. You have a past singularity and a future singularity, and there's not really an asymptotic boundary. And so, okay, so you're a little bit stuck at that point, and you have to think of some idea that will help you proceed. And so I will talk about two different approaches that I think people discuss more generally when thinking about cosmology and holographic descriptions. And so I'm going to call them the local approach and the global approach. And so the local approach to holographically describing this cosmology is to say, well, imagine some observer in this Big Bang, Big Crunch space-time. So in the entire history of the universe, this observer will only ever be able to measure or have access to some finite volume of the cosmology. So they're existing only for a finite proper time. And so it's kind of irrelevant what's going on in the far reaches of the universe where nothing could possibly causally travel from here to here, or the reverse. And so we could maybe say, well, in terms of just describing the physics that an observer could access in such a cosmology, we should be happy with a description that includes just some large enough finite volume region. So we could try to find a holographic description of at least a part of one of these cosmological spacetimes. And so I think that is not so daunting, because so one thing you could do is just consider different ways of completing this space-time. So there's the homogeneous and isotropic way where you get the full global cosmology. But then I could do something else. Like I could take a finite volume patch of this cosmology and then just say, okay, I'm going to throw everything else outside of that patch. Maybe on some spatial slice, I just get rid of everything outside and say, this is going to be empty. And then we study the evolution of that universe. And so you can actually relatively easily find solutions that correspond to that. And so a way to construct them would be to take a part of your FRW cosmology, so this is like where the observer was living, and here's some finite volume bubble. So you can take this part, and then outside it's empty, and it's spherically symmetric, and so the outside better look like some short shield, and it would be short shield ADS if we're working with negative lambda. And then you could try to patch those together somehow. And so it turns out there's some relatively simple exact solutions you can find. So if you have some arbitrary matter and radiation inside the cosmology, then all you need is a shell of dust. And if you choose the density of the dust correctly, then you can satisfy the Israel junction conditions and find a nice solution where inside is your FRW, outside it's a black hole. And now it's just an asymptotically ADS spacetime. And so, because it's an asymptotically ADS spacetime, now you could say, oh, that should be dual to some kind of special state of the CFT. So, it's obviously going to be some interesting high energy state. Because it's a black hole spacetime from the outside, this is some black hole microstate, if you want. And so these kind of, out of all the possible black hole microstates with a given energy, maybe some subset of those would correspond to these cosmological spacetimes. So, yeah, again, you might be this, from some perspective, if you could find such states and study them, this should be completely satisfying, because you don't expect the world, the observer that lives here to care really what's happening out here. So that would be potentially then a way to study the cosmological physics of whatever solution you're interested in by doing ordinary AES-CFT. Yes?
I'd like to just ask about maybe the distinction between saying, okay, I have CFT, which is dual to some AES with a particular effective field theory that lives in it. And so it makes sense to study that effective field theory in its own right, and it also has cosmological solutions. At that level, I don't really need to do the work of like cutting out a piece and embedding it into AES, right? That argument is fine even at that, right? And I'm trying to understand what we're gaining by doing this, because it's sort of a kinematic state, right? I mean, it's a little bit like, I could also entangle a bunch of particles in AES with a closed universe, right? And say, okay, now the entanglement wedge includes this closed universe, which could be arbitrarily large, and then claim victory and say, now we have a fundamental description of the dynamics of this closed universe or something like that. And I don't think we want to do that. Right?
Yeah. So what the advantage would be is what I have in mind is being able to tell you specifically what state of the CFT to look at that would correspond to the physics of this cosmology. And then if you knew exactly what state it was and you knew what CFT you're looking at, then in principle you should be able to answer questions. I mean, okay, so I'll get to this in the next slide. I mean, if we had the full power of AES-CFT to answer bulk questions, we could then ask questions about the nature of the Big Bang singularity, or what the physics would be, what really happens at the earliest times in such a cosmology. So you could, in principle, ask questions that go beyond your effective field theory by relating them to some CFT questions.
I doubt that. I doubt that. I don't think so, right? Because do you think that we can resolve the Big Bang and Big Crunch singularities in a closed universe where I've got a couple of particles that are entangled with a bunch of particles in AES? Just because it's formally in the entanglement wedge? Do you think we can actually construct a unique state that that's...
I mean, let's see. So let's say I have just a regular, and we're describing a black hole in AES, or so a two-sided black hole. I mean, do you think that we can? So if I ask about questions about the black hole singularity, these are hard from the CFT point of view, but are you saying you don't think in principle I could?
Well, the distinction that I would draw is like, are we making use? So if I make a black hole and asymptotically, that means you make a one-sided black hole and let it evaporate.
Yeah.
Maybe it's a small black hole, right? So here I'm not needed. I don't need to, do the dictionary. I don't need to use the dictionary except near the boundary. I can translate the in state into a CFT state. There's a very simple dictionary there, and then the out state again. But because I have the CFT Hamiltonian, I can evolve on the CFT side to do the calculation that my gravity calculation would have actually gotten wrong. Right? If I try to do the same evolution of the body, I would have gotten the wrong answer. So, but the extra sort of the added value comes from actually being able to use the CFT Hamiltonian. Anytime that we're talking about stuff that's sort of going on behind the horizon, the only way that we can claim to access that is by using the bulk equation of motion in some way, by already assuming something about the bulk.
Yeah, I don't think that's true. So let me just give an example of, let's say we want to construct this state. So one kind of simple cosmology would be just to have matter, and so if I just have a bunch of heavy particles, and that's my matter, and then I have the negative cosmological constant. Okay, so I'll propose a sort of construction of a state like that. And so let's start with a Euclidean path integral where I have the CFT on a sphere. And so now what I'm going to do is just insert a whole bunch of operators at this polar region. So I want to insert operators in such a way that, so the kind of standard thing of inserting a heavy operator and then that giving rise to some heavy particle that lives in the bulk. Okay. And so if I do that, then Now I've got some Euclidean solution with all of these heavy particles in there. So it's a specific state depending on exactly how I insert these operators. And then, so the Lorentzian picture is, so here's the spatial slice at the time symmetry point, and that includes particles in some region, and then it's empty outside. And so if I do that in the right way, then I can make these particles approximately homogeneous and isotropic, and then the Lorentzian solution will be something like this. And so, but now, because I have this Euclidean construction, then there is a very particular state of my, the construction is giving me a state of my effective field theory, and so that would be like some more information than just, you know, here I don't know what this, if I just drew this, I have no idea what state of my effective field theory I have. Kind of, you would say, well, it depends on whatever initial conditions you put. But if you have some Euclidean construction, then in principle you know everything. And then also I think you can use this Euclidean picture, that's a simpler way to calculate stuff about the cosmology. If I want to probe the region in the cosmology, then I could just use HKLL in the Euclidean picture to relate correlation functions in this middle region to some boundary correlation.
I just meant that HKLL uses the bulk equations of motion. So
Okay, but maybe a souped up.
A different way of saying this is that this is all in the same relatively patch. So
Okay, let's not use HKLL.
Yeah.
Let's just calculate, let's just calculate 2-point functions. So there's various kinds of 2-point functions that would probe this geometry, and so it's just calculating these boundary things. And I think if you calculated enough of them, then you would learn about the physics of this full space-time. And it's in a different way. Like you would be able, in principle, to get exact answers.
Well, for instance, if you had a two-sided black hole,
Yeah.
instead of a one-sided black hole, then boundary to boundary, the 2-point function where you put an operator on one side and one on the other would probe something about the big crunch or big
Right.
singularity.
So that's an example of what I would have in mind. Right?
Just like Steve.
You have a Euclidean construction there. You can put operators on either side. There are singularities that, at least if you allow looking at analytically continued correlators that show up that tell you about the black hole.
I would have said this constrains the dictionary. There's a kinematic duality that has to do with like having a state on the boundary at one time and asking what could that possibly be dual to, and we know that that's actually not unique. I mean it's it depends on the code subspace and so on that we choose, but of course it has to be consistent.
Yeah.
But you're not. It's like it's just like evolution in the wheel-to-wheel patch. I mean that evolution, I don't think you get any more information just from knowing that it's somehow dual to a CFT state. Once you fix your code subspace, it's just what the bulk theory says it is.
I mean, it's not obvious that every possible state of effective field theory could be realized. I mean, it's
That's true.
In writing down the solution here, like this could just be, could be in the sort of solution space swampland where this is not realized in an actual quantum gravity theory.
No, so I don't deny that this is useful, that you can actually construct a state.
Yeah.
I'm just not sure that you're learning something about the dynamics in the bulk from the fact that this happens to be dual to one CFT state that's not even evolved. I mean, we're not using the CFT on top.
Yeah, I guess you're not going to learn. I mean, in the regime where effective field theory is valid, you could probably just learn do effective field theory, but to say this is a valid state in some complete theory, and then also I think to say, well, maybe the possible initial states are constrained somehow. Even at the background cosmology level, it looks like sure you can construct that, but maybe actually there's some subtle constraints about correlations of fields that are possible that you thought you could get anything because you're doing effective field theory, but actually what could come out of a past singularity in the real, like all the possible constructions you could come up with is constrained somehow, so you always have certain kinds of correlations. Anyway, so let's, I think you could probably gain value just by the existence of a real construction that, that uses quantum gravity. It may be challenging.
This is related, by the way, to Stefan Critique's recent paper. Theoretic construction, I mean, preparations of states like that have sort of two different interpretations.
Yeah, it's in some way, I guess. Yeah. But it's I feel like, okay, maybe we can talk about it. I feel like it's a little bit different in philosophy from this because this aims at actually predicting that for another universe, but the kind of same kind of puzzles might arise.
Yeah, I think I didn't mention this point. You might be worried about some kind of bag of gold type paradox where there'd be more entropy inside the cosmology than in the CFT state. A lot of cases, basically, if you think about the spatial curvature, if that's at all negative, or even in the flat case, most of the time you find that the black hole entropy exceeds the entropy of the stuff in the cosmology, and so it doesn't seem like you would have a problem faithfully representing the cosmological physics in the CFT. There's just lots of states at high temperatures in the CFT, or large energies in the CFT.
Using the same method, are you saying that it will be impossible to prepare a state for which this is not true?
So, I mean, I would worry if this is not true. So there are examples where this is not true. If I have flat cosmology and the size of my bubble is like it's parametrically large, so it's some power of L ADS over L
And you can still prepare it through Euclidean.
I'm not sure if I can then. So
Yeah, that's interesting. So
yeah, there are later we'll get into issues about whether the thing that you think you're preparing is actually the dominant saddle, and I think you can run into problems. By the way, this was so people tried to do this for de Sitter. Inflation in ADS CFT was a paper back in the 2000s where they tried to do this for de Sitter, and there the Euclidean construction just fails. Marelf and Fu had a paper a little while ago just noticing that if you try to do this Euclidean construction, this domain wall kind of self-intersects, and so it does not, I mean, that's an example where it does not seem like the naive construction of the state that you thought you had works at all, and so it is not clear at all that you can do the same thing and have de Sitter inside and have a legitimate state of a CFT. Okay. Yeah, maybe, okay, just very briefly, I think an interesting thing about this construction is that there are many possible ways to complete the space-time. So I just picked one with a shell of dust and the same effective theory outside, but you could have, I think you could have even some other effective field theory outside and some domain wall, and then that would give you another description of this bubble of cosmology in a completely different CFT. And this is sort of related to stuff that I think I talked about last time I gave at Berkeley seminar. So there are these papers that I wrote talking about how bubbles of a space-time, if we're just interested in the physics inside those bubbles, there are probably many equivalent descriptions where the outside is different but the inside is basically the same. So that says that the holographic description of the cosmological region, maybe the actual degrees of freedom are not very important, and it's more to do with something like the long distance entanglement structure or correlations or something. Okay, some interesting lessons from this approach. So in these constructions, the cosmological physics is often behind the horizon of black holes or also in a Python's lunch. So that suggests that physics would be very difficult to extract if someone just handed you the Lorentzian state. But as I mentioned, if there is a Euclidean construction of a state, then we can do a lot better. It's also interesting just to notice that in these constructions. The Big Bang is basically just a special case of the black hole singularity. And so any progress toward understanding black hole singularities in ADS-CFT would then potentially help us understand cosmological singularities. Okay, so let's talk about now a different approach. So this is kind of ugly because it, from the start, like breaks the homogeneity and isotropy that we all liked in cosmology. I mean, I guess you could take a limit of where the energy of the CFT state goes to infinity or something and then get the whole cosmology. But let's say we want to try to describe everything globally. And so not introduce an asymptotically ADS boundary in our Lorentzian picture. So there's another interesting observation, I think originally due to Moldasian and Maus, that with this global cosmological space-time, sort of this one, there is in a sense an asymptotically ADS boundary hidden somewhere, and where it's hidden is in imaginary time, either plus or minus infinity in imaginary time. So these are examples. This is like radiation plus negative cosmological constant. And so the analytic continuation to imaginary time has this cosh instead of the cos, and then for tau equals plus or minus infinity, that behavior is asymptotically ADS. Okay. And so that is intriguing, and it's strongly suggestive of how we might try to come up with a construction of such a cosmology. So the fact that you have this asymptotically ADS space-time in the Euclidean picture suggests that there should maybe be some Euclidean ADS-CFT where you start with a pair of 3D Euclidean CFTs. And so if you could find a holographic construction of this thing, which is kind of like a wormhole because there's two disconnected boundaries, then you could think of that Euclidean construction as preparing the state of your cosmology that you're going to evolve. So kind of like Hartle-Hawking, except instead of no boundary, there's this ADS boundary, asymptotically ADS boundary. And so if you could achieve that, then you would just use, the cosmological observables would be related by analytic continuation to the observables in this picture. And so again, you could presumably compute whatever interesting cosmological correlation functions you wanted by translating them to the Euclidean picture and then computing them there. And so then the question is, how do we actually do that holographic construction? And as Moldasian and Maus originally pointed out, this quickly gets you to this factorization puzzle. Now, in the last few years, we've made a lot of progress in understanding how to get wormholes out of holography. So, I mean, the puzzle is that this solution, if you use that to calculate boundary-to-boundary correlators, then you find that there should be some correlation between your two CFTs. And if you just have simply two Euclidean CFTs that aren't connected to each other or interacting, then there wouldn't be any correlation. So you have to kind of put that correlation in somehow. And so that could be through considering some kind of an ensemble of theories, or possibly through some interaction that you're introducing between the theories. So I wanted to explore that, and so recently with Alex Maloney and his student Barrage, and my student Abhishek Sahu, we've been exploring this idea of the wormholes and how to construct them holographically in the context of 3D gravity. And so here the nice thing is that we have complete analytic control over a big space of cosmological solutions that are fully back-reacted. So the kinds of solutions that we can describe explicitly in 3D gravity would be solutions where we have matter plus cosmological constant, and the matter is just a bunch of heavy particles. So that's what I've drawn here. This is the cosmology. You've got a bunch of heavy particles coming out of the Big Bang and crunching, and then the Euclidean picture is that these massive particle geodesics connect the two boundaries. Okay. And so we can explicitly construct the solutions. So the way to do that is to start with a spatial slice of such a cosmology. Okay. And so I'm going to tell you the construction for a globally flat cosmology with heavy particles that are in a square lattice. Okay, so this is a very special matter configuration. So the way to do that is to think about, so these spatial slices are two-dimensional. So we're going to start by thinking about the hyperbolic plane. And this is a geodesic square, these are geodesics. And so I can think about this particular geodesic square. It has angles that are less than 90 degrees. And so what I can now do is think of a big lattice of where I glue these things together. Okay, so I can glue any one of these squares smoothly to another one of those squares. And so I just do that in a big square lattice. And so that results in a completely smooth space-time except for some conical deficit singularities. So you get something like that, that's your spatial slice. Everything is smooth going around here, but there's a conical defect there. And so we know that we can solve Einstein's equations at that point by inserting a particle with a certain mass. So in every one of these defects, I now put a particle with a mass given by the defect angle divided by 8 pi g, and then I find the solution.
Are we making this topology not closed?
I'm imagining we could either have an infinite lattice, so just globally flat cosmology, or I could periodically identify and make a toroidal universe that would be closed.
Oh, I thought maybe just the conical defects would be enough to kind of close off.
Yeah,
That's even with the local.
No, so yeah, I can. It depends on the construction. So this construction really just gives you something globally flat. We can also have ones that are closed. So it just depends on exactly how much mass you put in there.
Yeah, I would have thought you can dial this mass, like just dial the conical defect and you can get what you want.
Yeah, you can get lots of different cosmologies.
And you're choosing to dial it in such a way that it sort of looks on a coarse grain scale, which just.
Yeah, I mean, I thought it's an interesting one to have. You know, it's an interesting point that you can start with locally negatively curved space and then still get flat cosmology by just choosing the masses correctly. So at large scales, yeah, this is, if you wanted to approximate this with the Friedmann equation, then you would be using the flat space Friedmann equation.
Right, but like any other flat cosmology, it's sort of infinitely finely tuned in some sense. Like the energy density on average has to be exactly the right.
Yeah, let's see. So, for this construction, I guess if you, sorry, I mean, I can change the, I have one parameter here, so I can change the deficit angle.
Yeah.
And then that will, bring so that changes the distance between the particles and their masses, and so the density ends up being the same.
Oh, the distance between them you can't
So I can, once I choose my geodesics here, then that fixes the distance. So the shorter the distance, the smaller the deficit angle, and the smaller the
I would have thought you can fix independently the size of this squarish thing, and then also the mass or the conical defect you put on each.
Can't you dial the distance between the world lines and the masses of the world lines?
Yeah, so you like the thing you can do, your parameter basically is which geodesics are you choosing. And so I'm assuming the symmetry, the square symmetry, and so, sorry, I should go all over here. So I have to choose 4 kind of symmetrical geodesics, okay? And so once I make that choice, so that's what determines this distance, okay? But it also determines the angle there. Okay, so the closer I get it,
If you're not going to do many copies of this together, it determines the specific deficit angle that you need to achieve, is that what you're saying?
Yeah, gluing 4 copies together. So, I mean, the construction is just taking these squares and then gluing them together. And so the deficit angle is going to be 2 pi minus 4 times this angle.
The point is just that the symmetry group, the Z cross Z symmetry group is only consistent with a flat, like flat topology. It's not consistent with a sphere, right? Or well, it could with a, you could have it, I guess, with like a finite discrete thing on a sphere, but.
Well, yeah, I think they're just asking whether there's 2 parameters to
Square
control or
lattice.
1, but there's only one parameter to control. Yeah.
But in general, if you were willing to have a bit less symmetry or just a different symmetry or something, then you could have.
Yeah, I mean, there's tons of solutions that break this symmetry. Like actually, you can just arbitrarily start gluing together. You pick start gluing together hyperbolic polygons, and then there'll always be some particular choice of mass that works for the vertex to solve Einstein's equations. And so there's all kinds of solutions you can generate this way, but I'm just focusing on some symmetrical one. Okay. Right. So that's the spatial slice. And then the point is it's locally hyperbolic. It's locally still just hyperbolic space. And so it's very easy to construct the global solutions because we just multiply by some cosh for the Euclidean one or cos squared for the Lorentzian one, and then add the time. So if this d sigma squared is just all of hyperbolic space, then this is just ADS3. But now we have the d sigma squared is just locally hyperbolic space. So these geometries are locally ADS3, and if we have chosen the mass correctly, then they're also like global solutions. Okay, so we have some solutions. And so now we want to ask whether there's some like more detailed CFT picture that we could surmise based on these solutions. So these are kind of interesting because we know explicitly what the matter is, and so we also know kind of what to do if we want to get a heavy particle world line through ADS. We have lots of examples of that, and the construction is just that when you have a heavy particle world line ending on your ADS boundary, that corresponds to some operator insertion. And so this suggests that for every pair of world line endpoints here, we should have a pair of operator insertions. So it's not just 2 CFTs, it's 2 CFTs with a whole bunch of operators inserted. Now that so far is just a completely factorized expression, and so again, you might have to invoke some type of ensemble in order to get this wormhole, or that could be an ensemble of CFT data or some self-averaging thing. But I wanted to suggest something interesting that is does not require us to consider an ensemble of CFTs. So the fact that we're inserting a bunch of operators here, that gives you a different kind of ensemble that you can think about, and that would be to just consider an ensemble of the insertions. So if I look at this, well, maybe I don't know exactly what particle that is. There might be lots of particles that have a similar mass, and so maybe the CFT construction is not exactly just inserting some very particular operator. We could imagine summing over the insertion in a correlated way. So I insert operator I here and operator I here, but then I sum over I. And so that would be a way to at least give you something that's not factorized and possibly give you a construction that could correspond to this wormhole.
So I'm a bit confused about this. So you're evaluating a correlation function independently in CFT?
So I am evaluating, a sum over a bunch of different correlation functions, and the correlation functions differ by which specific operator I'm inserting. So maybe there's a bunch of operators that correspond to particles with roughly the same mass, and up to 1/c corrections or something. So maybe I'm summing over. I'll do a very explicit example in a minute, but maybe I'm summing over which operators I'm inserting, and so then this thing is like an ensemble of correlators rather than a correlator in some ensemble of CFTs. Okay. So the fact that I'm summing over this is kind of telling me that construction would be giving me some mixed state where I don't just have a particular particle state here, I have a mixed state with a lot of different possibilities that I'm summing over. So this is like a construction that's giving me a mixed state cosmology. Yes?
What happens to the leading contribution? So usually the wormhole is a sub-leading.
Yeah. Right. So the question I want to ask, going like as we go on here, I'm wondering if there's a way that I can get this wormhole as a leading contribution. So,
Okay, so you want
so
it to be a leading.
for now, yeah, we have to worry about sub-leading contributions. Any construction like this might have other saddles. Those other saddles might dominate. But I'm wondering, can I actually get a situation where this thing is really the dominant contribution and the other ones are suppressed? So that would be, then I would be feel happier that I've actually constructed something that's going to give me cosmology.
Yeah, this is actually what.
Yeah.
Here you have an infinite number of particles, right?
Of possible, I could do the torus if
There's
that's
some-
better.
Well, yeah, because I'm just curious whether there's some minimum amount that you need in order to sort of resolve the Mouse paradox.
Yeah.
I guess. Is
Yes, I'll get there. So this is the question we want to explore. How much of this, like what we're doing is injecting some entropy into our cosmology, basically. And then a question is, well, how much entropy do I have to inject in order to actually have this as the preferred saddle? And so we might think, okay, maybe we'll need a lot of entropy to have the cosmological spacetime be the dominant saddle, or to have this wormhole be the dominant saddle. In a Lorentzian context, when you have a pair of CFTs, we know that you need a large amount of entanglement between the two CFTs in order to have a connected solution be the dominant part of the state. And so the Euclidean version of that would be something like you need a very large amount of correlation between this side and this side. That would manifest itself as a very large amount of entropy in your cosmology. And so how would we get a lot of entropy? Okay, so the thing that we then explored was to imagine that okay, if I want to really get a lot of entropy, I want these particles to be super heavy so that they're actually above the black hole threshold. So that the kind of best way to get entropy in this context is to have fewer particles, but have each particle be very heavy, so that I get up into the region of the density of states where we have a lot of states that I can sum over. Okay, and so that was the idea. Instead of just some kind of arbitrary coefficients. Okay, so we had this thought we could kind of do a canonical ensemble of operator insertions. So for each pair of operators, I sum over all the possible operators, and I control that with a Boltzmann factor. Taking this beta then to be small, I would expect that the ensemble is dominated by heavy states that would then look like some black hole microstates. But what we're doing here is constructing just the kind of thermal state black hole. So the picture would be we do this, take beta sufficiently small, and now my spatial slice, instead of just having a heavy particle, it actually has some black hole. So far, this would be like a black hole without any particular commitment to what happens beyond the horizon of this black hole. So just like in ADS, when we think about the thermal density matrix, that's describing a black hole exterior, and there's different purifications that we could have that have different stuff happening beyond the black hole horizon. So that's what this is. We could, if we want to, extend this to choose a kind of a purification for this cosmology. So there's something that's kind of analogous to going from the mixed state black hole to the thermofield double. And so that's the following. So if I, instead of summing over operators at these points, I just stick in a tube, cut a little hole out of one CFT and a little hole out of the other, and then have a tube connecting the two sides. So we know that that tube, if I could integrate out the CFT fields on that tube, that will have the effect of giving you the sum over insertions. So the tube is kind of like a way to, I mean, you're adding some CFT degrees of freedom here in a particular way that will give you back this ensemble picture once you integrate things out. But this one here is not really an ensemble at all, it's just a CFT path integral on a specific geometry. And so I'm going to argue that, so doing that, if you take that Euclidean geometry for your CFT, and then if you find the corresponding 3D gravity saddle, which sort of fills in the region between the two, to give you a particular kind of wormhole, what that gives you is this thing here, but now every little black hole has a second asymptotic region. So you can just do this gravity calculation. Find the saddle, understand what the spatial slice is at the time symmetric point, and then you find adding the tubes has the effect of adding the second asymptotic regions. Yeah.
Is this feature connecting back to the idea that you can just have something like an ensemble by having a coupling between the two?
Yeah. So right. So we've, in a sense, we've replaced an ensemble. We had an ensemble that was giving us this mixed state cosmology, and we've replaced the ensemble with an interaction, or we've generated the ensemble with an actual interaction by introducing some auxiliary degrees of freedom. And now the dual is something where instead of having just a mixed state cosmology, each black hole has this second asymptotic region that it's entangled with. Okay, so this is kind of like in the end, it's like a pure state cosmology. And you know, a nice thing about the tubes that we've added is that now we can actually slice the CFT path integral and say, oh, this is generating a state of a bunch of CFTs, generating an entangled state of a bunch of CFTs. And so we now have a Hilbert space for our cosmology to live in. So the summary is, by the time we got here, we're just doing this Euclidean path integral that generates a state of a bunch of CFTs on circles or spheres. And then that's an entangled state, and then that would be, we claim, dual to this cosmological space-time that's filled with black holes. Each black hole has a second asymptotic region. Yep.
So I must be getting my pictures wrong.
Yeah.
Can you explain where the second asymptotic region is in the Brown pictures?
Yeah, so when you slice through, let's think of, this is the CFT construction. The wormhole saddle that's going to correspond to our cosmology is something where you can imagine filling in the space between the planes, but not filling in the tubes. Okay. So that's a Euclidean geometry. It's time symmetric, and we're going to slice that in half to understand the initial data slice for our cosmology. So, all right. So we slice that in half. So our gravity solution is filling in. We're going to slice this in half. Okay, and then the slice goes through all these tubes. Okay, but the tube is like a place where the CFT is, and so that should be an asymptotically ADS boundary. So in the gravity solution, anytime you hit the CFT, you've hit some asymptotically ADS boundary. And so the fact that you've got a bunch of, naively your slice looks like this, but those circles are actually a place where the CFT lives, and so that's at infinite. That's like an asymptotically at ADS region, so it's kind of.
So the first asymptotic region is kind of like the planar part of the brown sheets. And the second asymptotic region, there's like infinitely many of them, and they correspond to these red circles here on the right.
Yeah. Yeah, let me draw, I thought this might be a little bit more illuminating. So this is the sphere version. Okay, so here's a CFT path integral. And yeah, instead of having actual tubes, I've just cut a bunch of holes out of the sphere. Okay. And so that constructs a state on a set of CFTs on a circle. Okay, so we've got this entangled state of all these CFTs on the circle, and then the dual of that is then a thing whose spatial slice looks like this. It's a sphere, a bunch of black holes, a bunch of second asymptotic regions, and then it turns out there's kind of, if you were living in this part, here you experience a big bang and a big crunch. So it's a special example of a multi-boundary wormhole. It's not so exotic, but definitely people have considered Euclidean path integral constructions of these entangled states that are dual to multi-boundary wormholes, but this multi-boundary wormhole has a kind of interesting interior that happens to look a little bit homogeneous and isotropic on large scales. Yes?
I kind of asked you this before, but especially for the closed universe case, do you know that the free energy calculus works out so that when it is a connected geometry, that the dominant solution is just one big?
Yeah, so let me just say this, okay. So the advantage, once we've got this picture, so this is a really completely well-specified situation where I have like, I'm gonna do the CFT on this geometry, I'm gonna find the gravity solution that corresponds to this cosmology, but then I can also find other saddles that preserve the same symmetry and compare the actions for these saddles, okay? And so what you find in the end is that there's something like a Hawking-Page transition. So as I make the size of these spheres bigger, or as I make the size of the black holes bigger in the cosmology, at some point there's a critical radius of the black hole above which the cosmology thing is the dominant saddle, as far, for the saddles that we've actually been able to compare. But indeed, as we expected, you do need a really large amount of entropy. And so that's reflected in the fact that your black holes have to basically be ADS scale black holes. Okay, so there's these really big black holes that are separated by a distance that's not much bigger than their radius. And that universe is going to be a cosmology that will correspond to a dominant saddle of this Euclidean path integral. But if you wanted to, if you thought about the solution where the black holes are smaller, or just you have a bunch of particles, then that solution is going to correspond to some subdominant saddle. That was the, okay, so I think that's what I have here. So, right, so for smaller black holes or particles, the cosmology is like a rare part of the wave function of the universe. But because we have this Lorentzian picture of all these entangled CFTs, then maybe we could actually imagine projecting now do some projection that would keep the cosmological part of the wave function and throw out the part which is just a bunch of disconnected ADS spacetimes.
Sorry, I think maybe I missed this, but it sounded to me like both the saddles that we were discussing were still wormhole saddles.
No, yeah, so we're confirmed. Yeah, let me say that the comparison is between a saddle where you sort of fill in the region between these, so that would be the wormhole.
Yeah.
And the other saddle we think of as what if you fill in the tubes instead, and then fill in this top region and the bottom region. And so that is a saddle that is like the below the Hawking-Page transition saddle, where if you slice through that one, you just get a bunch of copies of ADS. So it's very analogous to Hawking-Page. One thing gives you a connected solution, the other thing just gives you a bunch of copies of ADS.
Shouldn't there also be a saddle when data is very large that corresponds to just having two completely disconnected saddle and the tubes not even existing?
Well, see with the construction, like by the time I've got the tubes there, the boundary is connected, so the space-time has to be.
No, but to get this tube picture, you start from a sum over OI.
Yeah.
I'm just saying that sum over OI, that sum over I technically just has correlation functions and two disconnected CFTs.
Yes.
And that's a good approximation when you have very few terms in that sum. And when you have beta very large, I imagine you have very few terms in that sum, no?
Yeah,
So
that's right.
when you have beta very large, would it not be that this tube picture wouldn't even hold? Because you rewrote the sum over I.
Yeah, I thought the tube picture always gave you, like if I take a really long, narrow tube, that constructs something that's very close to the product of vacuum states, but there's still all these corrections, specific kind of corrections that would correspond to the infinite sum of insertions. So I think you can consider any beta, you can always have this tube picture. If the tubes are really long and narrow, then you're just going to totally be dominated by the saddle that fills in the tube.
Okay.
Okay, I'm basically, let me just, sorry. Let me just see if there were any lessons. So just some general lessons that I found interesting in this example that we did. So it seemed interesting that in this example, we had actually either the possibility of considering some kind of ensemble, where we just have all the operator insertions and we sum over them, and that was giving us this mixed state cosmology where we were kind of not having any particular thing behind the horizon of the black holes. But then we can also replace the ensemble with an actual, an interaction between the two sides, connecting two sides with tubes. That involved introducing some extra degrees of freedom into our half integral, and once we did that, we actually had a kind of pure state cosmology, and it lived in some Hilbert space that was the Hilbert space of these these extra degrees of freedom that we added in. That's a similar story to a bunch of work I did with Stefano and Peter and Brian, where there our starting point was just to take the two 3D CFTs and stick in some interaction from the start, and the interaction preserved translation invariance, and that was to have just a higher dimensional quantum field theory coupling those. Okay. Do we have like 3 more minutes? Or I don't know how.
No, we asked a lot of questions.
Okay, yeah. I just wanted to kind of advertise something that I find very intriguing, which may amount to nothing, but I was very struck by it, and so this is the fact that we've been talking about these cosmologies with lambda less than 0, and I was saying you get Big Bang, Big Crunch cosmologies, and in the simple ones where you just have matter and radiation and lambda less than 0, those never accelerate. They're always decelerating. And so naively, they're just not realistic kinds of cosmologies for our universe. But I think this is a little bit too quick. So if we ask about what are the generic cosmological solutions that you would get out of holographic gravity theories, then you have to realize that these holographic theories, they typically have very light scalar fields. So if you do ADS CFT, the standard dictionary says that for every scalar operator in your theory, so for every Lorentz invariant way of deforming the theory, there is some scalar field in the bulk. And there's a formula that tells you what the mass of those scalar fields would be, and it's this formula. And so if your CFT has any operators with dimensions of order 1, relevant or irrelevant, you're going to have some scalar fields in your effective theory whose masses are of order the ADS scale, which ultimately in these cosmology solutions are of order the cosmological scale. So ultra light kind of scalars. And so those will have some kind of a potential. And so our ADS solution that's dual to the vacuum of the CFT is a solution where the scalars remain at one point at an extremum of this potential that would have a negative value. So the negative cosmological constant means that this scalar potential has an extremum with some negative value. That's often, if you have any relevant operators in your CFT, then that would be a saddle. So you would have some negative directions and some positive directions. So that might be a typical situation. And so these cosmologies that just have matter and radiation and negative cosmological constant, they're cosmologies where we're forcing all of these scalars to just sit there, okay? But then if I said, okay, well, what are the generic kind of solutions that have the symmetries of an FRW universe? And so the generic solutions, cosmological solutions, would be solutions where we allow these scalars to vary with time. And so instead of just having a negative cosmological constant, we would have some type of dark energy that, you know, might be, say, generically start far away from that point. And interaction terms would typically make this thing go positive eventually. So we might imagine that the most generic thing that could happen is you start somewhere way off where the scalar is at a very high value of the potential, and then eventually it rolls down. Finally, it crosses the v equals 0, gets into this negative V region, and then we recollapse. Okay. And so the cosmology prediction for that would be that you have your Big Bang, your matter and radiation dilute, and then when the cosmological constant, or sorry, when the cosmological term starts to become important, it could well be that you're up here still in the positive V region. So that would then lead to acceleration in a lot of cases. And then eventually when you descend down here, you would get deceleration and crunching. Okay. So it's fairly generic. This is the surprising thing to me was that if you just think about what should you expect from holographic ADS cosmologies, I think it's fairly generic to end up with some late time acceleration because of the dynamics of these scalar fields. Okay. And so I was so struck by that, you know, so then if you observe acceleration, it seems a bit quick to just say, oh, we should now focus on positive lambda because apparently the negative lambda models that we actually have a lot of control over can also give you acceleration naturally in this way. So I was so struck by this, I wanted to...
I'm a bit confused, I don't want to take too long,
Yeah.
but why does it end up wanting to go back into a v greater than 0 region?
Yeah, because the decelerating part of the universe, the damping that happens in, so the scalar equation has a damping term, which has h. And so when you are accelerating, then the scalar evolution is the damped motion of a particle in this potential. As soon as you start decelerating, you get the anti-damped motion of a particle in this potential. And so you're suddenly gaining all this energy from the anti-damping. So yeah, that's the reason. I think I might have the equation.
I don't think scalar fields are all potentials.
Well, this is the equation.
Yeah, I know if you make a homogeneous approximation, but this is unstable, right?
Yeah.
It's the same.
Okay.
Reason that if you ran our revolution backwards and just changed the position of an electron,
Okay.
we would not get anti-inflation in the early universe.
So yeah, I mean, I guess let's see.
It's a highly, second law violating type of thing.
Okay, so you would get some inhomogeneities.
Yeah, but you don't. I don't think you care.
Anyway, I definitely don't care, right? So this is just at the level of
That's satisfying.
homogeneous and isotropic cosmology. This is what happens. But indeed, it's certainly true that when you start crunching, there's a lot of instabilities that happen, and you would generate a structure and all sorts of things. So yeah, I don't really care because we would not be there yet. So. Yeah, anyways, at this point I was like, well, is it possible that this is the real story? And there's like a totally obvious prediction then, if this is actually the story compared to positive lambda, this says we should just find some changing dark energy. And there's no reason why it should be changing slowly, so I wanted to just kind of rule this out by, looking at what observations were available and seeing, if we're pretty sure that dark energy has been constant up to 1% accuracy over the last few billion years, then I'd be satisfied that this is not really the story. So it was a little bit difficult to to like read into the cosmology literature, cosmologists often do silly things like look at the WCDM model
Why
and
did
then
you just say
constrain-
1%? Where did that come from? Why did you just say 1%?
Well,
Would you
okay.
expect that it's like completely in your face dynamical evolution? Like
So-
1% already is fine, is tuned.
Yeah, no, that's what I'm saying. I'm saying if we looked at the data and it suggested that the dark energy is constant at like a 1% level, then I would just say, okay, fine, it's lambda CDM.
Well,
Like this is saying,
maybe suggested at a 2% level, but why is that not good enough?
I guess what I'm saying here is that I don't see any reason why this wouldn't be 100% change in the dark energy over a cosmological time scale.
Exactly. Or in fact would have long ago started to sort of dominate the cosmological evolution. I mean, there's two things that can happen here, right?
Yeah.
One is that this going to, you know, going down this slope and then eventually hitting B equals 0.
Yes.
You hit B equals 0 much later than the current age of the universe, in which case this would kind of propagate like a cosmological constant. Or much earlier than the current age of the universe, in which case it probably gives you something that's inconsistent with what we've observed by a lot, not just by 100%. Right? To even like be anywhere within the ballpark of what we've observed, you already need to kind of tune it. You need to tune the time when it equals 0.
Yeah, no,
to be-
I think this thing tells you that this scalar evolution happens on cosmological timescales.
But what says that? So, what in your theory what do you mean by the cosmological timescale? Right? There's a current
So-
age of the universe, which is the timescale when we happen to live. Is that what you mean by that timescale?
Yeah, there's an ADS scale in these theories. So L is just a part of your theory. Okay, it's the ADS scale.
But L is 10 billion light years, or what is that? Like, what do you choose for that? Is it the current age of the universe?
So it would be, yeah, I mean, we could take the Hubble scale if you want.
When? The Hubble scale is time independent.
Okay, so in these Big Bang, Big Crunch cosmologies, then for most of the age of the universe, the scales are like the matter density and the cosmological, like the dark energy density is of the same order of magnitude. And that order of magnitude is the ADS scale from your theory.
No, I don't understand. The matter energy density changes very dramatically during the evolution of the universe, and so does the Hubble scale. So the Hubble
No,
scale
so,
is...
yeah, but this is the thing here. For a recollapsing universe like that, okay,
Yeah.
the Friedmann equation tells you that the matter density and the dark energy density is equal. in
At the
magnitude.
turnaround point.
At the turnaround point.
But why are
yes.
you choosing the turnaround to be now? I mean,
No.
what are you choosing for that?
And so that's true at the turnaround point, okay? But it's also true for most of the time. If I look at the total amount of time from the Big Bang to the turnaround point, for most of that time, the matter density and the cosmological constant density are of the same order of magnitude. So if I just go by time, I mean, there's a short amount of time where your matter dominated.
If that were true, then it would never behave like a cosmological constant, because then it would redshift like matter and radiation. I mean,
So it's
the
not really
flow of
behaving
matter
like-
scales like 1/a cubed, right?
Right.
And the cosmological constant. I mean, for it to cause any acceleration at all, it better not scale anywhere like that, right? It has to really be independent of the scale factor to a good approximation.
But it's not. I mean, I'm not saying it's behaving like a cosmological constant.
Right, but it
So-
can't behave anywhere similar to the matter energy. Those two things cannot, with time they have to evolve in a radically different way. Otherwise, one of them isn't matter, or the other one isn't a cosmological constant, even roughly. It can't cause acceleration.
Okay, so yeah, I'm not quite sure I'm getting your complaint. But like, we can just look at. So we have some potential, and you have. Well, let me say what we can do. So let me say what we can do. So, assuming let's say we have a picture like this, and the idea would be, okay, we're falling down maybe some gradient direction in a potential here, And so if I want to model that and constrain parameters, then we could say that at least in the relatively recent past, then we could Taylor approximate the potential. And you would have a current value of the potential energy, and you would have a slope of the potential. And then maybe further back, there could be higher order terms in the Taylor expansion that are important, but we're going to not worry about them. And so just in terms of comparing with data, then the point is, given this parameter, and the matter density today, and the Hubble constant, so those 4 parameters will give you some model value of a scale factor evolution. Okay. And lambda CDM is a special case where we set V1 to 0, and we set V0 plus E matter equals 1, or if with the right scaling. Okay. And so we could just look at this class of things, and what I would have expected would have been to see that maybe for models that fit the data, the evolution of this potential during the last 5 billion years is not huge.
Oh, last 5 billion years, of course. Nothing happened in the last 5 billion years. But I just mean that over the course of
Right.
I mean, in cosmology, we sort of think logarithmically in terms.
No, but I'm saying this is not what we found.
I see.
So what we found was that, in fact, the models that fit the data well do have a large amount of evolution of the scalar energy in the last 5 billion years.
Which data do they fit well?
Yeah, so we're looking at, I'm trying to use this Taylor approximation of the potential. And so what I want to look at are the best data that we have for the recent evolution of the scale factor. And that data includes supernova, redshift versus brightness, and baryon acoustic oscillations. Okay, so those are the 2 data sets that we looked at. Okay. And the, we figured out how to do these standard likelihood analyses that people do. So we used the data from the Pantheon plus cosmology papers. And we were able to reproduce their WCDM figures, and then we did our model. And so, yeah, let me just look at the blue ones. The blue one is the combined data set. And so we find that the lambda CDM is pretty, this is a 95% confidence interval. And lambda CDM is pretty far outside. And so what this V1 equals 1 means you've got an order 1 change in the energy density during a Hubble time.
I'm sorry, but 95, I mean, 2 sigma in cosmology is like, you're doing great.
Yeah,
So I don't think it's fair to say that lambda CDM is somehow under pressure from this graph.
I mean, I'm not saying, yeah, so I'm not concluding that lambda CDM is ruled out, but it was surprising to me that models with a large change in the energy density, I mean, the point of this was to convince myself that there's not really room for a large change in the dark energy density on the half the age of the universe. That's what I was expecting. And so the surprising thing to me was that there does seem to be quite a bit of room left for a significant change in the dark energy density. So I'm not claiming to have ruled anything out, but I find it very interesting that it doesn't seem like we're pretty sure based on this data that you have lambda CDM.
I'm a little confused about what V0 and V1
Yeah,
are.
V0 is the current value. It's what we would normally call omega lambda.
Sorry, about what we want is.
And V1
Is
is
that
the
related
slope.
to like W and WA or something like that? Or?
Yeah, so good. So V0 and V1 are actual parameters that you can write in actual effective field theory. W0 and WA are numbers that you add into the Friedmann equation to get a model that you can't realize using any effective field theory, but we do.
I
So,
agree.
Yeah. No,
But
a little bit less
I'm
right.
just trying to, you're certainly allowing W and WA both to vary, right?
Yeah, so let me give you a diagram. So there was a similar thing that got a lot of press recently by the DESI collaboration, where they did the same thing as this. Yeah, by the way, our stuff was pre-DESI, so not just ambulance chasing. Accident causing. You won't actually read our paper. Anyways, yeah, so what they did is exactly the same with a newer data set, but they use this W0WA model. And so that's basically you have rho matter over AQ plus rho lambda, and instead of rho lambda here, so the WCDM model says that you're going to put artificially a term here, which is A to the W plus 1. That's it. So W plus minus 1 is cosmological constant. Yeah. Okay. And so the WCDM, you just add this term to the Friedmann equation, and you constrain this parameter, okay, which doesn't have anything to do with physics, but it's something you can do. And then W0WA says, now instead of having a constant W, I'm going to allow my W to vary with A. So it's some equation that you could write down that, again, doesn't really have any particular physical origin. But they did that, and so they did W0WA, they made the same graph as this, and they found a result with a similar amount of significance. I think their result, depending on the data set, if they used our data, the result was less significant than our results, and if they used the newest data set, the result was more significant than our results.
Have you tried doing your plot for the newest data?
Yeah, this is on the list, so I don't think, I'm not sure if it's publicly available yet, so I think their paper has not been accepted, and they said they would wait, they would release their data when their paper is accepted.
Have you tried to get them to use your
Yeah, I want to do that. I mean, I don't really like spend my life doing likelihood analyses. so I mean, no, I think it would be seriously interesting for them to do. I mean, I feel like this is much more natural to do because oh yeah. So what did they get? Right there. Let me show you their. Okay, so W is basically like the ratio between pressure and energy density, and so you could just evaluate the time evolution in our model and in their model, and so their best fit model basically did, this is now and in the past, their best fit model did something very weird. So they've got W less than -1 for most of the evolution, and so I believe that just violates some energy condition, and so the fact that they find a model that has no actual physical origin and probably violates energy conditions, which fits the data better than lambda CEM, I don't think I
thought it's null energy condition, isn't it?
Is it? Yeah. Is it null?
It's something about this dominant energy condition. I don't remember if I was, but it's
isn't null energy condition in Friedmann that rho plus P is greater than 0 or something? Rho minus P.
I don't think so.
Sorry?
Yeah, not that I recall.
Okay.
I think you need a little more than that. But it still allows for some physical effects.
So if you look at W for our model, so we each have a scalar field. It's going to be physical. It does this. So it's not really. It's a separate slice in W parameter space. They're looking at a 2D slice, which is linear W, and we're looking at a 2D slice, which is linear scalar potential, and the W looks different. Yes.
I'm confused. So I think there's a whole industry out there, right?
Yes.
People who write down quintessence models and scalar fields and things
Yes,
like that.
yeah,
And they do it, unlike you, they do it without any pretense of like trying to get it from some fundamental theory.
sure, yeah.
But at the level of like, once you're interested, like matching to the data, I feel
Yeah,
like that
yeah.
work should have been done for you. Like,
Yeah, that's what I thought too. And there were papers, Linda did this in 2003, exactly this. And then the data weren't very good. And they found, in their paper, they have a plot of the distribution, and they have the V1, and it looks like this. And so there was a hump at like V1 equals 1, but then the hump wasn't really much bigger than the V1 equals 0. So, and then, you know, after that, I find that most of the quintessence literature is not doing this thing where they just tailor expected potential and look at recent data. What they are doing in almost all of the papers is to come up with some model like e to the beta phi minus e to the alpha phi, and you know, they like this some particular potential, and then they look at, you know, both early universe and late time stuff. And then they're trying to constrain parameters in there, whatever potential. So we didn't find anything more recent than like Linda 2004. Maybe there was one other paper in there. So it was not convincing to us. So that's why we decided to do this. Or really, it was Chris Waddell. I should give all of the credit for actually doing this. Because I kind of sent him off to like look at what's in the literature, and then he came back and said, "Oh well, here we can just use this data and try to do it ourselves." And I said, "Are you sure?" And he said, "Yeah, I'd like to learn about cosmology." And then, you know, at some point he sent me an email and said, "Okay, I did it, and V1 is 1.2 plus or minus 0.3." And then I said, "Are you sure?" That's important. Oh, why? Anyway, yeah, there's. I mean, I'm excited because I think there's all these telescopes that will just like do better than what we have now. So I mean, like the fact that there's some room here for something dramatic like lambda CDM isn't the answer is pretty cool. But you know, there are also a huge number of phenomenological considerations that would have to be dealt with if you have this light scalar sitting around in nature. That's challenging to explain why doesn't it interact with the standard model and give you fifth forces and things, and where are all the light scalar particles that would be associated with that field, and like all sorts of things that you would have to deal with. In a way, they're higher order effects. Okay, so that was pretty focused.
Since there was a lot of questions, I think we should just thank.
Are you here tomorrow as well?
Yeah, I'm here for part of the day tomorrow.